Hello and welcome to the channel. Here is another Canadian problem with another tricky solution from its authors. The link to the previous Canadian task should appear on the top. This time, as you can see, it is not about factorials, but about integral parts. Probably to make it easier, instead of just saying solve the equation, the description clearly indicates the absence of solutions. Whether or not this really helps, you will soon find out, but before that, let me go through some useful properties of an integral part. Again, as I mentioned in one of the previous videos, for me integral part is what is called floor nowadays. The greatest integer not exceeding the number. That's how it was understood for 2 centuries, while any attempt to redefine the meaning of an established term leads to ambiguity and confusion. At start, integral part applies only to real numbers. So letter A will always stand for a real number. And the integral part of A is by definition the greatest integer not exceeding A. Lower square brackets indicate that the truncation is always applied down toward the lower integer. Property 1 follows straight from the definition of an integral part. So integral part is an integer. It is not greater than the number. However, the following integer, which is integral part plus 1, is greater than the number. Property 2 is also quite obvious. If m is an integer not exceeding a number, then m does not exceed the integral part of the number. Indeed, m is an integer not exceeding number a, while the integral part of a is the greatest integer not exceeding a. Therefore, m is not greater than the integral part of a, and property 2 is proven. Property 3 is an opposite to property 2. If m is an integer which is greater than a, then m is greater or equal to integral part of a plus 1. So now m is an integer greater than a, while integral part of a plus 1 is the lowest integer greater than a. Therefore m must be no less than integral part of a plus 1, which is what property 3 is about. What the solution really uses is property 4. If n is an integer, then the integral part of n times a is greater or equal to n times the integral part of a, and less or equal to n times the integral part of a plus n minus 1. To prove property 4, let's take the inequality of property 1 and multiply all 3 parts of it by n. Next, we apply property 2 to the left part of the obtained inequality. The left-hand side, n times integral part of a, is an integer, which doesn't exceed n times a. Therefore, according to property 2, the left-hand side must not exceed the integral part of n times a. Then we apply property 3 to the right part of the double inequality. The right-hand side, n times integral part of a plus n, is an integer, and it is greater than n times a. Therefore, according to property 3, the right-hand side must be no less than the integral part of n times a plus 1. Therefore, the integral part of n times a plus 1 is no more than n times the integral part of a plus n. After subtracting 1 from both hand sides of the obtained inequality, we get another inequality containing integral part of n times a. By merging the obtained inequalities for the integral part of n times a, we get the double inequality claimed by property 4 and complete the proof of the property. Now it's time to get back to the given equation, and I will copy property 4 for convenience. This will give you an advantage to year 1981 contestants, so I invite you to pause the video and try solving the equation on your own. So let S be the sum in the left-hand side of the given equation. Can you guess what is going to be next? Of course, we apply property 4 to each term of the sum S. Next, we of course add up all the inequalities and get S in the middle. Both the coefficients for the integral part of x represent the sum of powers of 2 from 0 up to 5. The powers of 2 form a geometric progression with ratio 2. So the sum is 2 to the power of 6 minus 1, or 63. There is also the sum of 3 terms, which can be viewed as the sum of 6 terms starting from 0, where each term is 1 less than the corresponding term of previous sum. So we subtract 6 from 63 and get 57. Now we can wipe out something we no longer need and copy the last obtained inequality to the top. This inequality may already remind you something, but in order to make it more obvious, I will rewrite it as S equals 63 times the integral part of x plus r, where r is a non-negative integer not exceeding 57. Of course, this is division with a remainder. Here S is the dividend, 63 is the divisor, integral part of x is the quotient, and r is the remainder. There could be also attempts to change the meaning of the division with the remainder, but for me the remainder is always non-negative and strictly less than the divisor. In our case, that would mean that r is non-negative and doesn't exceed 62. However, the actual range for r is shorter. Try to continue from here. Here comes a splendid idea. Let's find the remainder from division by 63 of the number 12,345, found in the right-hand side of the given equation. If this remainder happens to be more than 57, this will be an unbeatable evidence that the equation has no roots, and the problem will be solved. Whether or not the calculators were allowed at the contest, I'm completely sure that the contestants were familiar with the long division. So let's use the long division as well.